guys, welcome back to STEM Superstars. My name is Callista, and with these videos, we will be going through the AP Chem curriculum in the perspective of an AP Chem student, and hopefully get that 5 on the upcoming AP test. So, in the few first videos of this channel, we'll be going over some things that are just the basics of chemistry and some things that I think are very important to just build a proper foundation in chemistry. So, in this video, we're doing significant figures, precision versus accuracy, and then just some basic conversions. So first, significant figures, or sig figs. What are significant figures? So they're just the digits that we include in numbers to ensure accuracy and less rounding errors, because we know that one of the biggest sources of error now is just rounding. Like, if we have a really large number, like pi, and then we round it to 2 digits, like there's obviously going to be some rounding errors there. So some rules for significant figures are that middle zeros are significant, trailing zeros are not significant unless there is a decimal, leading beginning zeros are not significant even with a decimal, and all non-zero digits are significant. What about scientific notation? You just ignore the times 10 to the power of whatever part. Just use the number in the beginning of the scientific notation. So I'm going to show you a couple examples with these rules because I don't expect you to understand what I just said just now. So practice problems. How many significant figures in 7.2 times 10 to the third? So as I said, when it comes to scientific notation, just ignore the times 10 to the power of 3 part and just cover that and just look at 7.2. So if we go back to our rules right here, all non-zero digits are significant. If we see 7.2 is just 7 and 2, those are both non-zero. So if I were to ask you how many sig figs in that number, you would say, right, you would say 2. Second, how many significant figures in 387? Again, look back here. All non-zero digits are significant. 3, 8, and 7 are all not zero. So if I were to ask you how many sig figs in 387, right, 3. This one gets a little bit harder. How many sig figs in 207? We know that all non-zero digits are significant, so 2 and 7 will both be significant. That's 2 so far. But then how do we account for this 0? Also in the rules, we say that middle zeros are significant. So this 0 is in the middle of 2 significant numbers, so that must mean, yes, 0 is significant in this case. So how many sig figs in 207? 3. How many significant figures in 100 with a decimal point at the end? Remember to look at that. We know that, again, all non-zero digits are significant, so the 1 is significant. But then we look at this, trailing zeros are not significant unless there is a decimal. Trailing zeros are just zeros after a non-zero number. So there are 2 zeros after this non-zero number, so we must think that they're not significant. However, there is a decimal there. Therefore, they are significant. It doesn't make much sense, but as long as this is mostly just memorization. Just memorize these rules and you should be fine. Since there is a decimal, there are 3 significant figures in 100 with the decimal on it. How many sig figs in 0.000034? We know that in this rule, beginning zeros, so just the zeros that lead up to a number, are not significant even with a decimal. So even though there is a decimal, all of these zeros are not significant, and only the non-zero digits are significant. So if I were to ask you how many are in this number, you would say 2. And then how many significant figures in 100? Although this may look the same as this question over here, it's not because it doesn't have a decimal. And since it doesn't have a decimal, these 2 zeros are trailing zeros, and they are not significant. Because if you go back to the second rule, trailing zeros are not significant unless there is a decimal. So, they're not. So how many sig figs in 100 without the decimal? 1. A really important concept in chemistry is knowing how to do calculations with significant figures. So, PEMDAS, multiplication, division, addition, and subtraction. How do you add and subtract with significant figures? So adding and subtracting is a little easier. You basically take the 2 numbers that you are adding and subtracting, and then take the number with the least amount of decimal places, and then carry that onto your answer. So say I have over here 43.13 plus 43.2. Which number, pause the video and then ask yourself which number has the least amount of decimal places. It will be 43.2 because it only has 1 as opposed to 43.13 has 2. Since it has the least amount, we would carry that into our answer. So if you pull out a calculator, or if you can do it in your head, 43.13 plus 43.2 is equal to 86.33. However, since we are using 1 decimal place, you would just round that to 86.3. It's kind of similar with multiplication and division. However, instead of it being with decimal places, you do it with significant figures. So say you have 4.37 times 0.00012. You look at the two things that you're multiplying or dividing, and then see which one of these numbers has the least amount of significant figures. Okay? Well, we can count with this one. Remember, all non-zero are significant. So 1, 2, 3. There are 3 significant figures in 4.37. And then over here, all leading zeros are non-significant. So there are only 2 significant figures. Okay? So that means that in our answer, we're only going to need 2 significant figures. If you put this entire thing in your calculator, 4.37 times 0.00012, you get 0.0005244. But since we're only using 2 significant figures, you only do 0.00052. That's how you round that. Now we're going to do some practice problems. So first, identify, is it addition and subtraction, or is it multiplying and dividing? And if so, what do you do? As you can see, this is addition and subtraction. That means that you do your answer based off of the amount of decimal places. So first, put it in your calculator. You get, if I'm not mistaken, 132.19. If you look at your things that you're adding, the number with the least amount of decimal places is 0.4, and that's 1. Meaning that in your answer, you would only have 1 decimal place. So you would round to 132.2. Next here, same thing. The least amount of decimal places is 2 decimal places because it's 0.03 as opposed to 0.076. So you put it in your calculator to get 60.106. Since you're only using 2 decimal places, you would just round to 60.11. It's the same thing for this. 12.34 plus 1.2. There's only, the least amount of decimal places is 1 because of the 1.2. So in your answer, you would round to 1 decimal place. 12.345 plus 1.2. To get 13.545. Since you're only using 1 decimal place, you do 13.5. Multiplying and dividing is a little harder, but remember, just look at how many significant figures are in all of them. Remember, all non-zero sig figs are significant, so 1, 2. Middle zeros are significant, 3, 4, and then all non-zero, 5. There are 5 sig figs in this. In this one, there's only 1, 2, 3. So in your answer, you would only use 3 significant figures. Put that into your calculator to get 54.733. 3 significant figures would be 54.7. Last question, 78.6 grams over 0.045 liters. There are 3 sig figs in the 78.6 because 1, 2, 3 are all non-zero numbers. And then there are leading zeros, which are never significant, remember? And then all non-zero values are significant, so there are 2. The least amount is 2 sig figs. So you would just put that in your calculator, 78.6 divided by 0.045 to get 1746.66667. Okay, you only need two significant figures. So how is this even possible to get 1746 to two significant figures? Well, this is when you would have to round a lot. So you would just round it to 1,700 because the trailing zeros are not significant and you would only have two significant figures, which is the 1 and the 7. But if you're doing like an actual problem, just ignore that part. You would only really implement this if they're asking you a question about significant figures. Okay, that's the whole thing with the significant figures part. Now we're going to go on to precision versus accuracy. So precision is just how much your answers agree with each other. And then accuracy is how accurate your answers are. Like, say this girl named Emma is measuring the temperature in one of her experiments. The temperature that she's supposed to get is 30, and the answers that she keeps getting are like in the 60, 61, 59 range. You would say that all of the answers that she's getting are pretty consistent, or they're pretty precise because they're all very close together, but they're not very accurate because they're very far from the answer that she was supposed to get. A really good chart for this is the accurate, precise, imprecise chart. So with this bullseye is showing it's accurate because it's supposed to be in the middle, and it's also precise because all the x's are close to each other. However, it's precise because all the answers are close to each other, but they're not near the bullseye. These are both inaccurate and imprecise because all the answers are so far away from each other, they're not agreeing, and none of them are near the target. This is accurate and imprecise because while they are near the target, not all of the answers are close to each other, so they don't even agree. Here's a practice problem. You are working in a laboratory and you are trying to measure the temperature of an experiment. You know that the actual temperature is supposed to be 107.5 degrees Celsius. In your first experiment, you calculate 60.8 degrees Celsius. In your second experiment, you calculate 61.1 degrees Celsius. In your third experiment, you calculate 60.9 degrees Celsius. Is this precise? Is it accurate? Or is it both? Okay, so think about what you're getting. You can pause the video to kind of tell. Okay, so in all of these experiments, you're getting the answer that's kind of close. Your answers are agreeing with each other. That would mean that since your answers are all agreeing with each other, that would be precise. That is precision. However, if you're supposed to be getting 107.5 degrees, then that's not very accurate because none of your answers are close to the correct answer. So I would classify this as high precision and low accuracy. Or here, this chart right here, high precision, low accuracy. Okay, now just basic conversions. So conversion is a very significant aspect in chemistry that helps people to do equations that pertain to various different situations. It's simple, just do a conversion factor. Just take what you have, line it up with what you want, divide with what you had, and whatever it is that made that conversion true. I do not expect any of you to understand what that sentence just said. Just take a look at the example and go with it. Practice problems. Convert 5 milligrams to grams, and convert 10 milliliters to liters, and then convert 1024 kilograms to grams. So this is an example of a conversion factor. So say you have 5 milligrams, and you want to see how much that is in grams. A simple way to think about this is write down 5 milligrams. See, I wrote down 5 milligrams. And then you want it in grams, okay? You want it in grams, so then write grams right next to it. And what do you want to get rid of? You want to get rid of milligrams. So write milligrams under it, okay? Then write values that make whatever of these equal to each other. So if I have 1 gram, how many milligrams is equal to 1 gram? 1,000. So I'd write that there. And then what is this just saying to you? To do 5 times 1 divided by 1,000. So that would mean that 5 milligrams is equal to 5 times 10 to the negative third grams, or just 0.005 grams. Another example. Remember, so basically just write down what you have, then what you want right next to it, and then what you want to get rid of under that. Another example. Say you have 10 milliliters, okay? And you want to say I have 10 milliliters of water. I want to know how many liters is 10 milliliters, okay? So I want liters instead of milliliters. So what am I going to do? I'm going to write liters next to it, okay? And what do I no longer want? I no longer want milliliters, okay? So I'm going to write milliliters under that. Now, what exactly makes this equal to each other? If I have 1 liter, how many milliliters do I need to equal 1 liter? 1,000. Okay, so just do 10 times 1, because this is just telling you this is also telling you 10 times 1, and then divided by 1,000. So that's 0.01 liters. Perfect. One more practice problem. Say I have 50 grams. And say you have 50 grams of copper sulfate. Crazy amount, but you know. And your teacher is asking you, how many kilograms is 50 grams? How are you supposed to solve this? Okay, so you have 50 grams. You want that in kilograms. So what are you going to do? You're going to write kilograms next to it. What do you no longer want? You no longer want grams, because now you want it in kilograms. So what makes this true? Okay, 1 kilogram is equal to 1,000 grams. So just do 50 times 1 divided by 1,000. So 0.05 kilograms. The only downside to that is that you have to remember kind of those basic conversion factors, like how many kilograms are in a gram. But that's kind of how you convert the two. Anyways, that was the first video going over significant figures, precision versus accuracy, and basic conversions. And I hope that it was a good simplified version. I hope that you understood everything that happened here. And stay in tune for the next video that will probably go over density, what is a mole, and molar mass. Bye.
Like and subscribe for an easy 5. Also comment any discrepancies or questions regarding the vid.